I use Python. I've been using Python for a while. I'm a Cython core dev for a while. I do trainings and consulting in that area, and I actually joined Trust You in 2017, and I'll quickly show you what that is as a motivating example for the talk. So this is what we do at Trust You. So when you look for a hotel in Google, for example, they give you a lot of information about that hotel, including, it's a 4-star hotel, people rate it pretty good. When we click around in that information somewhere, then you might find that this information down here was provided by Trust You. Okay? So we're the ones who know how good a hotel is. And how do we know? Well, we collect hotel reviews from the whole internet globally at a global scale. So lots of data that we sit on, and that means we're pretty much a big data processing company. We do text analysis in more than 20 languages, so lots of things there. Then we make this out of the data. Okay? So here you see our so-called meta review. We use all the reviews that we collect to summarize them and to provide information like, this hotel has a great location, has a great pool. The rooms are not as good as the pool, but it's an excellent romantic hotel, stuff like that. And we can even tell you how hotels differ, what makes a hotel special compared to other hotels. And if you want to make use of that, you can go to trustyou.com, type in a hotel name, and we'll tell you everything about that hotel that you need to know, based on what actual guests to that hotel said about it. So Trust You definitely loves Python, we love data, and all of that is based on the Python big data ecosystem. Here's a couple of tools that we use at Trust You. It's just a selection, and since I'm the one giving the talk, I'm the one selecting the tools that I show here. There are definitely a lot more, but stuff like NumPy, obviously, SciPy, scikit-learn, we use pandas, we use LXML for getting the data in, and many of these tools, actually most of these tools, are either partly or even completely implemented in Cython. So when you look at the Python data ecosystem, what you can see is that it's an ecosystem because it's integrated, okay? So the thing is, it's such a great ecosystem because it has an excellent data integration layer. All of these tools can share data through NumPy. NumPy is their way of passing around data, of processing data, of sharing data, passing data into native libraries. So NumPy integrates the data in this ecosystem, but Cython is the one that integrates code. It integrates external code, native code, into the Python ecosystem. So what is Cython good for? Well, as I said, it integrates native code into Python. That's one of the use cases. Many people use it to speed up Python code in CPython. And some people use it to write C without having to write C. Okay? It's actually very common, especially in the scientific Python community, where many people are not trained programmers. They are programmers by need, meaning their goal is to solve a problem, and the only way to solve that problem is by programming. So they learn programming, okay? And they're not software engineers. They are programmers by need, okay? And that is the reason why they're using Python. That's also the reason why they're using Cython, because Cython makes it easy for them. Both Python and Cython make it easy for them to solve their problems with programming. Basically, we write C so you don't have to. So why Cython? It's the fastest way to integrate native code. It's a pragmatic programming language in the same way that Python is. Basically, Cython is Python with C data types. So it compiles to C, But you write Python code, okay? It's a pragmatic programming language that makes it easy for you to solve your problems with it. It's production proven, it's widely used, and it's really all about getting things done. So it allows you to keep your focus on the functionality without having to care too much about all the boilerplate that you would have to consider when you go native, when you implement something in C, in C++, in Fortran if you want, in any of those low-level languages, okay? The cool thing is that it allows you to move freely between Python and C++ or C in your code. So you can jump right into C without leaving the programming language that you're using, without leaving the Python world, basically. So it's as Pythonic as you want, but it can be as low level as you need. Okay, that's enough for an introduction. So here's a demo. I'll just clear the output. Who of you has never used the Jupyter Notebook? Wonderful, there's no one. Perfect. I love it. It's a great tool. And it's a support for Cython. So all you have to do to use Cython in Jupyter is load x Cython. Well, you have to pip install Cython first, obviously, but afterwards load x Cython and you have it in your notebook. These are the versions I'm using. Not exactly the latest Python version. I think there's a newer beta already out there, but this is new enough. Also, the latest unreleased Cython, GCC 7, something like that. Oh, and obviously, since it compiles to C, you need a C compiler, okay? So that is a dependency that you have of build time. So in order to build your packages, you need to throw them into Cython, compile them to C, have the C compiler compile them to a native library, and then you can ship them from there. Okay, so quick intro. You know the math library in Python, so I import the sine function, and sine of 5 is this. That's simple. I can do the same thing in Cython, and all I have to do is put this little line up here to tell Jupyter that what I'm writing here is not actually Python code, it's Cython code. Otherwise, exactly the same code, but when I run it, I take this out, it doesn't output anything. Why is that? Well, what Cython does is it compiles the cell to an extension module, to native code. Okay, then it imports that module and executes it. But Jupyter can't see what code is in there, it just sees what the output of that code is. And there's actually no output here. But when I say print, then it prints it. Okay? So the way Jupyter works is the last thing that falls out of your code basically is shown. Okay, and there's nothing falling out of the code here because it's, it's an extension module, it's an external module that I'm running. Okay. So this is just still plain Python code, didn't change anything in there. Now the cool thing in Cython is I can use the Python math module and the sine function from there, which is a Python function, but I also have access to everything that's C. So I can just take the sine function from the libc math header, okay? All I have to do for that is I C import, so C import is a static import in Cython. I C import libc math, take the sine function from there and actually assign it to a variable. And since that's a Python variable, okay, sure. Like this? Okay. So since I'm assigning to a Python variable here, Cython will automatically decide that it has to convert this C function to a Python function for me, to a Python callable, and it does it. It wraps it for me. And since I assign to a global variable here, I can use it from my Jupyter notebook, and I can call it from Python. So I'm calling the libc sine function from Python here, from Jupyter, simply by, well, assigning it to a Python variable. And this is how Cython works a lot, how really Cython code works. you do stuff in C, you do stuff in Python. Whenever Cython sees that you're doing C stuff and pass it around into Python, it converts it for you and vice versa. Okay, so it takes care of that. So it works for simple functions, for anything that's representable in Python. I mean, the sign function takes a C double. C double is equivalent to a Python float object, so that's easy to convert. For anything that's more involved, I can use explicit wrapping, and this is how it looks in Python, in Cython, sorry. I can write a Python function here. Cython allows me to type my arguments, so I can say the input is actually a C double, which Cython then unpacks for me automatically from whatever I pass in. And then below that, I call the C sign function on that value and return the result. And since this is a Python function, the return value of that function is an object again, and the C double that comes out of that function is a return value. It's converted into a Python float and returned. Okay? So you can execute this, call this Cython function that I created here, and it gives the same result. Now, a very nice feature of Cython is the Cython -a option. What it does is it compiles my program and then outputs an HTML snippet for me that Jupyter can display, which shows my code the way Cython has seen it. Okay? And then when I click on one of these lines here, it shows me that, the C code that generated for it actually calls the C sign function. I'll scroll that up a bit again. Calls the C sign function on the X variable, and then uses a C API function of CPython to convert the results from a C double to a Python float object, okay? In order to return it from the function. So this is really helpful, and one more thing that it gives me is it shows me yellow lines, and these yellow lines have different shades. Okay, this line is darker than that one, and the darker a line is in yellow, the more Python interaction there is going on. So when I'm writing my code and I want to make it fast, I want to make it, give it to C speed, get it down to C speed, then what I want is as little yellow as possible, because if I have no yellow in there, if all lines are actually white, then I know that what Cython's executing there, or what Cython's generating there for me, is plain C code and no longer code that uses the Python C API to do something with objects. Okay? So this is a really nice way to optimize your code to understand what the compiler makes of it. And as I said, click on a line and you can see the C code generated from it. Really helpful. Okay, this is still pretty boring because I'm only wrapping a plain C function and doing nothing else. The cool thing about Cython now is that I can do way more in that native layer. I call the C function, but I can also I can calculate x squared, for example, before I do that. And then when I can show you what that does, you can see this line is all yellow. When I click on it, you can see that the computation here, x squared, is actually done in C. Okay? So that means that I can make this wrapping layer, the layer between the native code that I'm executing, the native calls that I'm executing, and the Python API can be as thin or as thick as I like. And I can put anything in there. I can do pre-computation, post-processing of my data. I can do multiple calls in a row, all in my little Python function, and Cython is going to translate all of them to C. Okay? Which is a difference to common wrapper generators. So when I generate a wrapper for an existing C API, then what I get is more or less a one-to-one mapping. And the whole overhead of calling into this C API goes into Python. Okay? Here I can put it into C. I can just drop it into my Cython code, try to get a nicer Python API out of it than the C API, the underlying C API is, and just make it nicer, make it faster for me. Okay, this is how memory handling looks like. If you know bits of C, then you know malloc and free. So I call the malloc function. If I get a null pointer back, I raise a memory error, right? And this is also how Cython works a lot, how Cython code looks like. You mix C and Python, right? In C, you would maybe return 0 or something from your function, or -1, some error code or so. In Cython, I can just raise memory error, okay? Totally the thing that you would expect from a Python API. And I can put that in any place in my code because, you know, it's Python, except that it can use C at any point. Okay, C++. C++ is, oh, who in here likes C++? That's a good dozen people, maybe, a bit less than we have in this room. Okay, so I actually like C++, but only when used from Cython. I don't like writing C++ code myself. But C++ fits great into Cython because Cython is Python, so it's object-oriented. I can work with objects, I can call methods on Python objects, do stuff like that. I can pass functions around and all that. C++ is also object-oriented. So when I use C++ from Cython, it looks a lot like Python code. And that is nice. So all I have to do is I have to tell Cython that I want to compile my extension module here with C++ rather than C. That's what I do with this command line here with a compiler directive. And then I can use a C++ vector, for example. A vector is basically a resizable array. Okay, it's a resizable C array, more or less. It's very commonly used in C++ as a list, as a stack, anything that you can pass, put in an array. And so what I do here is I implement a Python function, which takes a couple of values, and then take these values and assign them to a C++ vector of ints. And as you can see here, the way I call it is I pass 3 numbers. And what Cython generates here in this line is it copies the numbers over into the vector. Because that's obvious from the operation, right? I create a C++ vector, I assign some Python sequence or iterable to that vector. What else should that mean than copying over the values? So Cython has this knowledge about how C++ APIs work, about how Python semantics are, and the language mixes both together and tries to make the best out of it and the most obvious out of it in the same way that Python tries to make the best out of your syntax. So I copy all the values, I push another couple of values into the vector, and then I can iterate over the vector using a Python for loop, print the values, and return the vector. And again, since I'm returning it from a Python function here, the return value is an object, and there's a standard mapping in Cython between vector and list in C++ to the standard Python data types that you would expect, meaning a Python list. Okay? So by returning a C++ vector from a Python function, what I get is a copy in a Python list. So I can compile this. Again, you can see the code here and the different shades of yellow. This is plain C++ code being executed here. There's some code that converts the C++ iterable here into the vector and copies it over. The iteration uses the standard C++ iteration protocol, even though it uses Cython syntax or Python syntax for the loop. And then when executed, I get all the values printed and returned as a Python list. Okay? Here's another little example. I'm using a C++ heap, and this is how you would define external functions. So Cython has these APIs predefined. It's quite a part of the STL. If you need to define your own stuff, this is how you would do it. You say cdef extern from some header, C or C++ header, some namespace, and then you just list the functions in there, and then Cython understands what that API looks like, and you can use it from Cython, and it safely checks and converts all your arguments going in and out. Okay, another little example. I'm going to wrap, Again, I'm going to wrap a vector in a Python class, and I'm going to wrap it as a heap. Okay, I'm using a C++ vector as a heap here. So I have push, pop operations. I can iterate over it, which in this case is structive iteration, and I have a wrapper. Okay, a wrapper function, a wrapper method that shows what's in there. And here's how you implement that. First thing you change is you use cdef class instead of class, which makes it an extension module. An extension type, An extension type instead of a Python class. Okay? And you need an extension type here because it internally wraps something C-ish, a C++ vector, and I'm really just using that vector as an instance attribute here. So I define my vector of doubles in this case as an attribute, and then I can use it in my code by storing the values in my vector in the constructor and calling the make heap function. So that creates a C++ heap for me. This is how the API looks like here. It looks a bit ugly, but from the Python side, all I see is that there's a float min heap class, and I can use it as a heap. Okay? Then there are push operations, pop operations. This is where I use the C++ API, and you actually don't see that I'm using C++ here, right? It totally looks like I'm using Python. Why? Because it's object-oriented. It's the same thing whether I use C++ or Python. It totally looks the same. It doesn't make a difference. The only difference is the types that C++ provides here and what Cython knows about. And Cython takes care of generating code from this that is adapted to the data types that it's operating on. Okay, so compile this, and then I can use my heap. I pass in a list of numbers, makes it look like this, can pop stuff from the heap, push to the heap, and so on and so forth. Okay? This is really all I need to do to wrap a C++ data structure in Cython. Okay. I have another example for you. I'm wrapping Lua. Who knows Lua? Okay, so you could say it's a tiny programming language, very commonly used for embedding something usually in C++, right? We have a huge C++ application, and then you need a scripting language in there and use Lua. So the implementation that I'm using here is LuaJIT. I'm compiling against LuaJIT 2 point something. And the first thing I have to do is, since this is no standard library, I have to declare what I'm using from that library. And this is how I do it. There are a couple of functions in there to create a new Lua runtime, to close it, to load code into it, and then, since it's a stack machine, to manipulate the stack to put data in and out. Okay, so this is how the Lua API looks like. Then I have a function, run Lua, which allows me, this is a Python function, right? So I can call it from Python, and it allows me to execute Lua code. That's the intention. First thing I do is, well, it's code, it's a string that I'm passing in there, so I need to encode it to bytes in order to be able to pass it into a C library. And then I create a Lua runtime that can fail with a memory error. Okay, fine, we've already seen that. And I load the code into the Lua runtime. There's an API call for that. I execute the code, and I process the return value. Okay, and you can see whenever something goes wrong, I actually just raise a standard Python exception. Okay, so I mix in some C call with some Python error handling here. I even use try finally around that to make sure I properly clean up my Lua runtime afterwards. Very common thing to do in Cython code, just like it is in Python. So I compile that, pass in my my Lua code. So this is just a recursive Fibonacci function in Lua, and calculates the right thing. And then when I time it, it runs for a while, gets repeated, and it takes about 6 milliseconds to execute and to calculate Fibonacci 26 recursively in Lua. Okay. Last thing, I'll just quickly go through this. There's a tiny change that I can make here. Since this is executing code in an external runtime, I can actually do this without holding onto the GIL. Who knows what the GIL is? A lot of people, not everyone. So the GIL is basically what makes Python fast. It's the global interpreter lock, which is used to protect the Python runtime against concurrency. And that allows very fast implementations inside of the runtime that doesn't have to care about special locking in any place. So it's very fast for single-threaded code that way. It's not that great for multi-threaded code. Okay? But for single-threaded code, it's as fast as it gets. So what I can do in Cython is I can actually release the GIL around the call into the external library. So while I'm executing my Lua code, I can free the GIL, because I don't need it at that time. There's no Python interaction at all, okay? All I have to change here is I can use a context manager in Cython, which says with no GIL. I put my code in there, and Cython will release the GIL before running my code block and reacquire it afterwards. I just copied this block over. It's the same as we had before, just executed without holding the GIL. There's one little thing in there which I implemented last night. You can actually raise exceptions from this code. That was not really that easy until last night. So this is not released yet, but it'll be in the next version. But it looks much nicer this way, so that's why I did it. Okay, so I compile this. And then I can use a thread pool executor to get threads here. And I'll run the whole thing 8 times in 4 threads. Actually, I only have 2 cores in my laptop with hyperthreading. So 4 threads is about as good as it gets, but don't expect 4 times speed up. And then when I run this, you can see that the first one, actually, I have to run it again, I think. Yeah, okay. First one is the one that uses multi-threading, so it calls the parallel Lua function, and the other one calls the first one, which does not release the GIL, and you can see that we get more than a 2 times speed up here. Okay, simply by running it in parallel, because we can free the GIL. Okay, and that's it. Thanks for listening.
Thank you. Let's get right to the Q&A because we don't have much time.
Can I just quickly answer? So yes,
yes,
it works for both. We actually generate C code that's very portable, so it runs in Python 2.6 through to Python 3.8, which is not released yet. Actually, 3.7 isn't released yet either, but like you get the C code once, you generate it once, and it compiles everywhere. Perfect. No differences. Well, GCC has more functionality than CLang, but that's debatable. Okay. Type annotations, yes, that's the usual question that comes. That's something I started implementing. It's kind of there. It's not complete. We have our own syntax for that, but you can use type annotations to a certain extent, and it's getting better over time. Downside of compiling C++. As I said, C++ is very nice in Cython because it's object-oriented, so the code looks very nice. C++ actually has a proper standard library as opposed to C. C has, something, but not really a standard library. C++ has a proper standard library. Cython understands, and it's very nice to use C++ from Cython, especially when you can use like the standard data structures in C++. Very nice thing. How to test Cython code? It's Python code, so you can always call the Python API that you're implementing using PyTest as you wish. Or fine, so you can generally use all the Python tools that you have for the Python API part. C++ namespaces. You've seen that I had this example here. Yeah. Well, I had this example here where I showed how the C++ API of the heap is declared. And that was actually using namespace std, standard namespace. So it handles C++ namespaces just fine. All you have to do is declare your C++ API in the proper namespace, and then Cython is going to generate the namespace code for you without you having to care about it. JIT compilation, yes, kind of, sort of, yes. So there is a decorator that you can put on a function in Python code that makes Cython compile the function at import time. And there's also, I think it's called Cython inline or so, where you can just drop in a code snippet as a string and compile that. So yes, can be used, although there are better tools for that. Okay, then we're through with the questions. One more thing, I put a couple of stickers in the back, so please take one or two or three if you want while you're going.